We are going to resume our discussion of projectile motion. And let me quickly describe the case 1 that we discussed in the last lesson. Case 1 simply means that we have a situation in which we are already at a certain height from the ground. This is the level, which may be ground level, it may be water below a cliff, and you are here at that height. And this is exactly the horizontal along which you throw an object. And when you throw this object, it follows a path which is known as the trajectory of that path. This kind of motion is one case of projectile motion in which the object is thrown horizontally. Initially, its velocity is all along horizontal, so there is no vertical component. In this kind of questions, as we did in the last lesson, most of the time the height is given, and with the help of that height, we can calculate the time it takes to reach the ground level. Usually we use second equation of motion for this purpose, and we apply it to the vertical motion because we know that initial vertical velocity is 0. And in order to calculate the velocity with which it hit the ground, we need to calculate both components. If this component is already known, the vertical component in the end can be calculated using the first equation of motion, because we know the time it has taken to reach. So V is equal to U plus AT, in which U will again be 0. So it will be a very simple equation to calculate the final component along the vertical. With the vertical component known, with the horizontal already known, we can calculate the resultant velocity with which it hit the ground. So this is the first case, and there are many questions in the exam in which we have to deal with this. The second situation is somewhat more challenging, and that is when we throw an object at a certain angle to the horizontal. Let's say this angle is already known, and suppose this is an angle equal to 30 degree to the horizontal, and when you throw an object at this angle, it will follow a path like this, and then it will hit the ground at the same level. So this object is obviously going to hit the object at a certain angle here, and like always, it will have a horizontal component of velocity and a vertical component of velocity in the beginning. A horizontal component of velocity a second or two later when the object is here. The horizontal component of velocity will be same at all positions. However, vertical component of velocity will change. As it moves up, the horizontal component of velocity remains constant, but vertical component goes smaller and smaller, and at the maximum height, suppose this is the point where the object is at the top of its trajectory, this is where only horizontal component survives and there is no vertical component now. But a moment later, when the object is here, it has the same horizontal component of velocity, and a vertical component of velocity is now developing in the downward direction, and when the same object hits here, it has that same horizontal component of velocity and the final large vertical component of velocity, which is same as it was here in the beginning. As we expect, when we throw an object up, it comes back and hit the floor with the same velocity with which we threw it up in the first case. So the object is taking a curved path, horizontal component of velocity along one direction, which is x direction, and vertical component of velocity is varying at a constant acceleration, which is 9.81. So like in the first case, we can define projectile motion again. It is a two-dimensional motion in which velocity remains constant along one dimension or direction, and acceleration is constant along the other. And acceleration is same 9.81. When we throw an object straight up, it is minus 9.81. And similarly, in this case, the value of g will be considered minus 9.81 when the object is thrown at a certain angle up. Now, what are some of the quantities that we might be asked to calculate about this type of questions? Before we attempt any calculation, I assume these values are known. Let's say this is 12 meter per second. This initial velocity with which we are throwing it is 12 meter per second. That means I know this component and I know this component. The horizontal component of velocity is 12 cos of 30 degree, and the vertical component of velocity will be 12 sine 30 degree. So I know the components. That means if I want to apply the equations of motion along the vertical, let's say I want to know what height this object achieved, the maximum height to which it rises. If this is the initial velocity at this angle, then this maximum height, capital H, is calculated using 2as is equal to v square minus u square. I have replaced s with capital H. This is the maximum height, the displacement of the object to which it rises, and this is minus 9.81. So you have 2 and this minus 9.81, this is H, and this V is 0 because there is no vertical component at this position at all, because the velocity is entirely along the horizontal. So although we have initial value of vertical component, which is 12 sine 30, but there is no vertical component at the object reaches the maximum height. So you are applying the third equation of motion to its vertical component alone. And this is the most important point about projectile motion, that we are considering one component of motion at in one situation, minus the initial component, which is 12 sine 30, which simplifies to 6. That means 6 meter per second. This is the vertical component of velocity. So we can take 6 square here. So when I simplify all this, this is minus sign gets cancelled with this minus sign. This is 36 divided by 19.6. So it simplifies to, suppose it is 1.8 meter approximately. If I make it something like 36 over 2 into, yes. So this is approximately 1.8 meter. You can check this calculation. It might be slightly different number, but this is what the formula is, and this is how we simplify it, and we get a certain number. that tells us what height it will gain, and then it will continue moving further to the right, because it cannot stop here. Its kinetic energy cannot be zero at the maximum height, because the horizontal component of motion still is there, and it will continue being there at all points. So kinetic energy is never zero at all these points, because there are velocities attached to the object, and even in the maximum height, the velocity, the momentum, it's not zero. Now, what time it has taken to reach the maximum height? In order to calculate the time it has taken to reach the maximum height, we can use first equation of motion, which is even simpler. So the time to reach the maximum height, time to reach the maximum height. Let's say this is a small t, and this can be calculated using V is equal to U plus GT. This is zero. For the same reason, we took V0 here, because the object has reached the maximum height. Its vertical component of velocity is zero. So applying this equation to the vertical motion alone, V can be taken zero. This U is 6 minus 9.81 T. So when I simplify this, T is approximately 0.65 second maybe. So you can check this calculation again. It simplifies to something like this. And in order to calculate the time of flight, the time for which the object has remained in the air, that is time of flight. Time of flight, let me take this as capital T. So capital T is simply 2 times small t. So that is approximately 1.2 the total time. It will take a certain time to reach the maximum height, and in exactly that same time it reaches the ground level. So 2 times the time taken to reach the maximum height is the time of flight, the time for which the object has remained in the air. Now, sometimes we are required to calculate how far it has gone from the point from which it was thrown. Let's say it's a missile and we want to know the range of that missile, how far it has hit the ground from the point of launching it. So this is the distance, usually denoted by x. This x is its horizontal range. So in order to calculate this horizontal range, we use a very, very simple formula, the simplest of all perhaps, and that is distance is equal to speed into time. And this is the only situation in projectile motion where we can apply this formula that you learned in your O-level classes. Otherwise, in all other situations you have seen, we are applying equations of motion, but this is a far simpler formula in which there is no acceleration involved. And this is because along the horizontal, the velocity has remained constant. And this is actually a constant velocity, the horizontal component of velocity. This will always be horizontal component of velocity. And since it is constant, no acceleration involved, so this time of flight, let me write it capital T, because this is the time of flight. This time. Of course, if I want to calculate half of it, I can use this time, but the total time is 2 times that, which I have denoted by capital T. So this all simplifies to 12 cos of 30° multiplied by 2 times small t, which is 0.65 second approximately. So you can check this number, but it simplifies to, and this is the distance the object has covered along the horizontal, which is known as its horizontal range, be it a bullet, be it a football you have kicked here at this angle, it moves in the air. And if we are ignoring the air resistance, this velocity has remained constant, this component I mean, and this component multiplied by the total time taken to reach here that we have already calculated. This gives us the range, the distance it covers along the horizontal. Sometimes they ask us to calculate the velocity during the flight. Let's say I know the total time it has taken is 1.2 seconds approximately. If I simplify this number, it gives us 1.2 seconds approximately. But what if they ask us to calculate the velocity of the object 1 second or 0.8 second or 0.6 second after we have launched it? So it may be here, it may be here, it may be here. During the flight, that velocity can be calculated. Let's see quickly how we do that. Suppose they ask us to know the velocity 1 second after the object is thrown. The object is thrown. Can we calculate the time now that it will take to cover that height, which is not maximum height now? Can we calculate the displacement now, the height it has gained 1 second after? The displacement can be calculated again. But obviously, final velocity is not going to be 0 now, because the object is clearly not at the maximum height now, because this 1 second is any instant, and the object is not stated to be at its maximum height. In the statement of the question, there is no hint that the object is at the maximum height. So 1 second after the object is thrown, it might be here. So let's see what is the time. Time is already given, 1 second. What is its velocity exactly? And by the way, this is the vertical component of velocity, not horizontal. That means this initial 12 sine of 30 will undergo some change, and it will become a different vertical component. And after I know that vertical component and I know this horizontal already, I can calculate the resultant velocity 1 second after I have thrown the object. So this is the vertical component of velocity. So I am writing this y with this. So Vy. This is u plus gt. The first equation of motion, v is equal to u plus at, is actually written in this form. U is the initial vertical component of velocity, which is 6. This I know. minus 9.81 into 1, because I know I'm considering it exactly 1 second after I have thrown. And this gives us a negative number. So this is approximately, if this is 9.81 and this is 6, this is something like minus 3.2, let's say, meter per second. You can check this calculation, what number you have here. But you have a minus value. That means the vertical component is already in the downward direction. If you know this to be 3.2 now, and you know this component already, which is 12 cos 30, this is same 12 cos 30, you can use these two and apply Pythagorean to calculate this resultant velocity. That means the resultant velocity 1 second after is now downward at an angle to the horizontal or to the vertical. That angle can also be calculated using trigonometry ratio, because you know this side of the rectangle, you know this side of the rectangle, so this angle can also be calculated, which I'll discuss in a few questions that we discussed as a practice, and I'll discuss in detail how we calculate the angles involved. But this is simple. It's not very difficult to understand how we can calculate the angle, because this is a triangle now. And if I know this hypotenuse and I know this base, I can calculate the angle here. So this is trigonometry basically. Now, what is the displacement of this object? Obviously, this is the displacement, because if this is the initial position and this is now its final, the straight line, the shortest possible distance between the 2 points, the initial and the final, is this line, which is this. So that displacement could be calculated using the second equation of motion, because I know the time. So S is equal to, even third equation can be used, because you know the final vertical component of velocity. Perhaps that would be simpler. So 2gs is equal to v square minus u square. And I know this is v, and I know u is this, this is u. The initial vertical component of velocity is this, initial the final vertical component of velocity of this, I mean v is this and u is this, and you use these values here, minus 3.2 squared minus this is 6 squared, and this is 2 into minus 9.81 into S. S is the displacement. This of course will be a positive number, approximately 9.5 minus 36, and this side is also minus 19.6 S. So when I take this difference, I have a negative number on this side, I have a negative number on this side, the minus sign will get cancelled, and I have a value for S. That will be the displacement of the object from this point. I mean the height at that point. So if this is the height of that point, how far it has gone from this horizontally? Along the horizontal, this will be the distance along the horizontal. And for this purpose, I will use x is equal to ut or vt, but this u or v has this meaning now, because the horizontal component of velocity is constant. This gives us this distance. So I know the height at which the object is at this particular instant, 1 second after I have thrown, and this is the distance it has traveled along the horizontal. So I know how far it has gone horizontally. If I use this and this, I can calculate its final position from the origin, from the point from where it was thrown. In fact, this is its displacement. This is the height at which it is at 1 second. This is the horizontal distance. This length is its displacement from the initial position to the final position. This is a straight line, although it has taken this path, but obviously this is its displacement 1 second after it has thrown. These are some of the basic ideas about this second type of projectile motion. We have discussed both type of projectile motions. We'll have a few more questions for discussion in the next lesson, and I'll share with you a few questions then. Until then, you go through all this, try to make sense. See you tomorrow, inshallah.